So thank you very much, Geronimo, and thank you to the organizers. It's a great pleasure to be here, I've enjoyed a lot of conversations in the last couple of days and the other lectures that I've had the privilege to listen to. And looking forward to talking with you all this morning and today in general. And when the organizers got in touch with me, they asked me to talk about thermalization and open quantum systems. And thermalization is a big topic, and you could talk about it in a lot of different ways and with lots of different connections. And open quantum systems is perhaps an even bigger topic, and you could probably give about 20 lectures on it. So what I decided to do is to pick up a series of topics in these sort of combined areas that connect to the other really nice lectures that we've heard earlier in the summer school, and perhaps also a little bit to the lecture that we're going to hear this afternoon. And I wanted to center this a little bit sort of around this question that Phil raised and that we discussed a little bit at the end of Phil's lectures on Friday, about when would you like to use an analog quantum simulator to do something, and when would you like to use a digital quantum simulator to do something. And of course, in connection with Steve's lecture yesterday, I'd like to ask the question as well, when would you like to use a classical simulator to do this, and where are your quantum simulators, whether they're analog or digital, not going to help you? So what I'm going to do is I'm going to talk about thermalization and out-of-equilibrium dynamics, and I'm going to talk about open quantum systems in such a way as to set the stage that in the second half of the second lecture, we can directly go into this question of what do we know at the moment about where, for out-of-equilibrium dynamics and systems that are looking like they're thermalizing, where can we do things with classical calculations, where can we do things, or should we do things with analog quantum simulators, and where should we do things with digital quantum simulators. So maybe just to motivate that a little more clearly, we have these things that we've seen in the lectures sort of up till now, and we know in general that in this community we have a lot of devices that we can use to do analog quantum simulation. And I should say mostly here I'm going to give a Blackboard lecture, but there are going to be some pictures and some plots and things like that we'll have up on the board at the side. I hope everyone can see the slides also. Of course, you have various different quantum simulators, and if you want to think about things working in an analog regime, there are lots of things, some of which you've heard a lot about already. We've heard beautiful lectures in the last 2 days from Misha talking about tweezer arrays, from Phil talking about trapped ions, and from Alicia talking about superconducting circuits. I'm going to comment a little bit on the fact that there are also, for example, neutral atoms and optical lattices that are sort of a slightly different sort of version of this. But these are all systems where we're getting pretty good at having microscopic control. And especially in the case of the AMO systems, we know what the underlying Hamiltonian is really from first principles. We can actually go from first principles understanding of the atomic physics and derive the Hamiltonians for the many particle systems under well-controlled approximations. And this then sort of, very nicely leads into studying those Hamiltonians in a highly controlled way with those experiments. And what we'll get to in the second half of the lectures this morning is that, in fact, you can do the same thing, derive models under well-controlled approximations from first principles, also for the dissipative dynamics of some of those systems. So in a sense, we're kind of starting here, thinking about these things as a theorist. You have these beautiful experiments with trapped ions, with neutral atoms, and with superconducting circuits. And in fact, you also have similar sorts of things when you deal with photons. So photons in different waveguide scenarios, or these beautiful sort of whole optical tablefuls of beam splitters that people have set up for boson sampling experiments and things like that. And in principle, there are other controllable solid-state systems that are gradually sort of entering here as well. And you think about connections with NV centers and photons, in V centers, talking to spins in different solid state compounds. So there's a lot of things that are sort of adding into here. These are all systems now where we have a decent deal of microscopic control, sometimes really good microscopic understanding from first principles, sometimes things, as Alicia described yesterday, that have been engineered highly in experiments so that we understand, to a very, very good approximation, the models that describe the behavior. And then basically, this knowledge of the Hamiltonian naturally motivates sort of studying sort of dynamics, also in particular dynamics of many particle systems. And that starts to get interesting because, of course, as we heard yesterday afternoon, there are some things you can do very well classically, but there are many open questions in 2D systems and 3D systems, and open questions even in 1D systems out of equilibrium in certain scenarios we would like to solve that we can't solve using any known existing methods on classical computers. In fact, what maybe sometimes gets missed now when we sort of start thinking about out of equilibrium dynamics with these systems and start talking about thermalization and information spreading in the way that I will in the next hour or two, is that, in fact, if you go back 20 years, people weren't trying to do so many calculations of out of equilibrium dynamics, and they weren't asking so many questions about thermalization and about integrable systems and quantum many-body scars. Actually, did Misha mention quantum many-body scars on Friday in his lecture? Sorry, I had a flight delay and came in a little bit late, so I didn't see that. Okay, so that's very good. So all of these sorts of things, in fact, have been very much strengthened in the last 20 years as theoretical physics questions, precisely because you have these experimental platforms that give you access to that out of equilibrium dynamics in a highly controlled form. So let me actually just expand a little bit for a moment on what I mean by sort of in a highly controlled form. And let me just sort of take, for example, something that we've seen in one form, namely in the tweezer array lecture that Misha gave on Friday. But let me take neutral atoms in a slightly different setting. And that is, let me take atoms and optical lattices. Who's heard and seen talks on atoms and optical lattices? Who hasn't seen talks on atoms and optical lattices before? Okay, so the idea here is you take neutral atoms, exactly the same sort of systems that Misha has in the tweezer arrays that he talked about on Friday. And then what you do is you take, for example, a set of standing waves of laser light where you sort of superimpose in 3 dimensions sort of laser beams like this in order to create in 3D a lattice structure, okay, where essentially along every dimension you get a potential for the atoms that looks like, for example, this sort of sine wave. The idea being that you sort of trap atoms in the lattice that can then, in principle, tunnel between neighboring sites, and so you have some sort of parameter associated with the tunneling. And of course, if you have multiple atoms on one site, there can be some interaction energy offset. So let me write bigger here. This is sort of J and U. In condensed matter, people call this tunneling T. But since we're talking about dynamics, we're going to do what AMO theorists like to do and call this J so that we can reserve T for our time parameter. So it's the difference in nomenclature that you often see there. So what was sort of shown back in 1998 is that if you start thinking about these sorts of systems, you find that under well-controlled approximations, going from first principles atomic physics, that you can build models that are typically discussed in strongly correlated condensed matter systems, like what I'm going to write down is indeed the first example that people talked about in 1998, which is the Bose Hubbard model. And these sorts of things people were discussing at the time actually to think about interacting disordered systems, the early days of thinking about things a little bit related to many-body localization. But the point here is that when you write these things down as condensed matter theorists, or you try to write down a Hubbard model to describe strongly interacting electrons in the solid state, normally these are phenomenological models that are sort of inspired as a way to have a toy model that describes the basic principles of the physics that you're dealing with. And the difference in these atomic physics systems is that you can start really from first principles and derive this under well-controlled approximations. And the reasons why you can do that essentially stem from the fact that what you deal with these cold atoms is atoms in a vacuum chamber. It's very dilute. So that means that, typically most of the collisions are two-body collisions. Three-body collisions are very rare. Okay, so it's two-body interactions. The single particle physics, okay, essentially involves kinetic energy. So if we write down the sort of the Hamiltonian for a single particle, you would say, well, I've got sort of p squared over 2m. I know the mass because it's an atom. All the atoms are identical. We know what they're like. Okay, we have also then some potential, which is normally generated by the laser light. This is normally done sort of as a light shift. The approximation here for a two-level atom is that we have sort of, we have a ground state and we have an excited state. What's happening is that the light is coupling it sort of off resonantly into the excited state. It's detuned by some amount delta, and it has some sort of coupling strength, which we give the symbol omega to, and in general, this is going to be an omega of x, okay? And this is a position-dependent Rabi frequency, and what you end up with, basically, is essentially a potential here that's proportional to omega of x squared divided by delta. Normally, when we write down the Hamiltonian, we get an omega over 2 in there, so we end up with 4 in the denominator. What's important here is that this quantity here, omega of x modulus squared, this is really proportional to the intensity of the laser light as a function of x. So if you want to create a potential landscape for these atoms, then the way that you do it is you create an intensity pattern, which you can project. We're doing this at the moment. We're creating an intensity pattern for light on the projector screen. It's a little bit more sophisticated in experiments, but not by much, and just has to be particularly highly controlled because the atoms are obviously very sensitive to it. But it means you can create tailored potentials. And so this is the single particle dynamics. And then the many particle dynamics have two things that you need to know. Firstly, that again, it's sort of always two-body collisions. In fact, in atomic physics, three-body collisions will often lead to two atoms going into a molecular state and the molecule and the remaining atom leaving the system because so much energy is ejected relative to the trap depths. But the fact the atoms stick around tells you that these are very, very rare in a lot of these scenarios, unless you go into particular regimes of resonances. So you have two-body collisions, and it's very low energy. And what we know from scattering theory and quantum mechanics is that collisions at low energies can be described by a single parameter, which is the S-wave scattering phase shift or the scattering length. And so essentially there is a single parameter and a universal effective scattering potential that you can write down that describes the scattering between particles at low energies. What do I mean by low energies? These things are laser-cooled and evaporatively cooled to temperatures of the order of nanokelvin, okay? And to collision energies that are normally several orders of magnitude below the sort of threshold for just having S-wave scattering. Okay, so you have a single parameter here, so you can really write down a many-body model from first principles, incorporating the interactions and the potential and the kinetic energy. The other thing that you know is that these atoms will either be fermions or bosons, depending on how many total electrons, neutrons, and protons they have. Why is that? Why does this composite object, or under what conditions does that composite object behave like a fermion or like a boson? So spin statistics, you just add up the number of spins. So that's where we get the, is it a fermion or is it a boson? Okay, so lithium-6 is a fermion, lithium-7 is a boson because of the total number of electrons, protons, and neutrons, and the spin statistics theorem. That's okay, but these things now approach each other and they come and they collide. Okay, so what's the condition on these atoms that allows us to say, well, it is either a fermion or a boson rather than a collection of fermions?
Depends on the energy scale. If it's low energy, then you can think of them as individual boson or fermionic particles.
That's right. So it has to be low energy, because obviously if these things came and collided and the atoms broke up, okay, then you would be starting to talk about things where you really had to worry about the constituents. Of course, I've just told you these things are so low energy that we've got just S-wave scattering, okay, and so naturally we're nowhere near the thresholds, normally even to excite an electron, let alone to break the atoms apart. So that's important, but that condition is fulfilled. But there's something else that's important in this as well. Sorry? Well, in principle, so you have in principle sort of Pauli pressure for fermions. This is absolutely true. But why can I treat the whole atom as a fermion or a boson rather than having to worry about having a collection of fermions? So the answer is it's the diluteness of the gas, again. The same thing that gives rise to the dominant two-body collisions. The typical size of the atom versus the typical length scale between the atoms. So if I took the density of these things, I took the cube root of the density to get sort of an approximate typical sort of length scale, sort of L, sort of the typical distance between the atoms. Okay, this has got to be much greater than sort of scales of the order of sort of the Bohr radius or so, or multiples of the Bohr radius that will give me the size of the atoms. Okay, and for people who are sort of familiar with sort of field operator notation, what I could ask is if I sort of create for example, a hydrogen atom that consists of a proton and an electron, and I ask what is the commutator between my annihilation operator for the hydrogen atom and the creation operator for the hydrogen atom, then I can write this in terms of creation operators for the proton and for the electron in an orbiting wave function around that. And I can show that this is essentially, this commutator is a delta function in 3D here, x minus x prime, plus some correction terms, okay, that come from the fact that I should have assumed, of course, that I had fermionic commutation relations for the proton or anti-commutation relations for the proton and the electron. And in the end, you see that this is small, provided this condition is fulfilled, that the typical distance, and that in this case, my choice of x minus x prime is much bigger than the size of the atoms. Okay. So it's subtle, but it works extremely well, and all of these things are correct to a very, very good approximation for these cold atom systems. Okay, and so now we have essentially Hamiltonians like the Bose-Hubbard model, that now what we've done is we've loaded this into the lowest block band of an optical lattice. We've got tunneling between neighboring lattice sites. We've got interactions when two or more particles sit on the same site. And these give us really sort of microscopic descriptions For a deep enough lattice, you can then say, well, there are sort of slight corrections with things tunneling over slightly longer distances and so on. These can be added in, but they are well known. These are very well controlled approximations. You know exactly what the next level correction terms are. So this type of thing, this first principles type of thing that you also saw Phil describe for ions, you saw Misha describe for neutral atoms in tweezer arrays. You saw also Alicia describe that you have these, you have superconducting circuits where you can go and engineer these things. This, of course, now motivates really the study of Hamiltonian dynamics, okay? And then you can start to ask questions about that. So when you look at out of equilibrium dynamics, you know, then what do we now expect in out of equilibrium dynamics? And of course, somehow, what we expect is in quench dynamics, which I'll define in a moment, we expect correlation spreading. We expect, you know, some sort of development of entanglement, and if you like, a scrambling of quantum information. We also expect, you know, thermalisation in some sense. This should relax to some sort of steady state. You don't expect oscillations that are going to go on forever once you put a system out of equilibrium. So how does it thermalize? Okay, how do correlations spread? How does entanglement grow? Scrambling of quantum information. The next thing is I've told you here why we know that we have first principles models here. Okay, but you know, the question is, do we have the same thing for open quantum systems? Okay, if I have now noise, or if I want to describe decoherence, how do I build a microscopic model for that? Okay, so how do we describe these things? And then, of course, you can say, well, exactly as I said at the beginning of the lecture, how do I ask the question of when should we actually study these quench dynamics with a classical calculation, for example, DMRG, okay? Or when should I use an analog quantum simulator? So when should I build my Hamiltonian in one of these highly controlled systems and do the calculation that way? And when would I rather do a digital quantum simulation? And so, of course, you saw the beautiful lectures from Dee yesterday morning on how you would go about coming up with algorithms for doing digital quantum simulation on a digital quantum computer. And so you always have that option. And of course, the question we're going to have to ask is, well, when do these analog devices, building the Hamiltonians, okay, even in the presence of decoherence and noise and calibration errors, when are they going to be competitive with or better than the classical techniques, based on the things that Steve was telling you yesterday? And when are current devices, you know, competitive with digital quantum, or indeed, when can you take the sorts of algorithms that Dee was telling you about yesterday and use those to simulate these dynamics better than you could on a current analog quantum simulator? What would the requirements for that be? Okay, and so this is what I'm going to look to cover in the remaining time over the course of the two lectures. So we'll start by talking about what we expect, what we mean by quench dynamics, what we think about in terms of correlation spreading, thermalization, scrambling of quantum information, and we will touch on where classical calculations then struggle. Then we'll look at descriptions of decoherence and noise in open quantum systems, in particular, where you can get these same sort of first principles models. And then we'll use this to judge how quantitatively reliable analog quantum simulation is, and use that to understand where it can give us quantitative answers that classical calculations can't, and understand what you would need to do in a digital quantum device in order to get near to this. Are there questions about the big picture? Feel free to interrupt, obviously, at any time. And good. So I'm going to move this up. And this down. Right. Okay. So quench dynamics. What do we mean, and why do we say quench dynamics? What do I mean by a quench?
Rapid change of a system's Hamiltonian, for example?
Exactly. So rapid change of a system Hamiltonian. Typically in this field, we actually use it a little bit more broadly than how it was originally defined in the following sense. What I'm going to do is assume that there is a state that is prepared at time 0, psi of t is equal to 0, okay, which is some state that I can prepare in an analog quantum simulator or in my device in general that I'm going to use to do the calculation. So this is normally going to be something that can be prepared in a controlled way, not necessarily as the ground state of a Hamiltonian. You may, for example, load atoms into tweezer arrays and put them all in a single internal state, and then you might turn on a completely different Hamiltonian. So this is going to be in an initial state, okay, which is not an eigenstate. Okay, and then we're going to turn on the system Hamiltonian H, and then what we're going to have is a time-dependent state that is e to the minus iht divided by h bar times psi of t is equal to 0. Okay, so far so good. So what do we now expect to have happen? So the first thing that is interesting is, of course, correlation spreading. So we might imagine here that we start, for example, in a spin state that has, say, all the spins pointing in a single direction, or we might start with atoms in an optical lattice so that I have sort of strong interactions and I load exactly one atom on every lattice site. Okay, in the strongly interacting regime, this will typically in the ground state look like a mod insulator. And so, so the question is, what happens now when I change the Hamiltonian so that this initial state is no longer an eigenstate, and I look at the evolution? And so what you expect is that excitations will form locally and they will start to spread through the system. And so one of the nicest sort of results in terms of this comes from back in 1972 in the paper by Lieb and Robinson. So this was in the Communications of Mathematical Physics. And this was 28, 251, 1972. And what Lieb and Robinson showed essentially is that if you start in a state where you don't have sort of correlations or where things are disconnected in some sense, that there is, if you have a system that has local couplings, so like in this Hubbard model where we just have sort of couplings between nearest neighbor sites, that essentially that there is in any sort of many-body system with local interactions that there is a light cone that essentially restricts the buildup of correlation. So if I ask, over some distance r, how strong the sort of buildup in time is of some correlation functions, then what happens is that at short times, those correlation functions are restricted to short distances. And what Lieb and Robinson showed is that outside of this light cone, that those correlation functions then drop off exponentially with distance. So that is to say, at any point in time, that the sort of correlation function sort of as a function of distance r is going to have the sort of feature that you're going to have significant correlations up to the sort of light cone, okay? So you have correlations up to the light cone and then exponential decay of the correlations outside of the light cone, okay? And so in fact, if you take as an example sort of spin-spin correlations, imagine that you have these things initially kind of decoupled, and you ask, for example, what is the correlation function sort of SZ at some distance, sort of some point in the system, x plus r at some time t, and you ask essentially what the two-time and two-position correlation is with that same operator at position x and time 0, then what they show is that this has to be smaller than or equal to some constant times e to the velocity times time minus distance. So you see here within some length scale sort of psi, this thing essentially, again, outside of the light cone defined by this, that this will then drop off exponentially. So as soon as the distance becomes bigger than the specification of the light cone, where v here is the light cone velocity. Okay, so this is known for systems with local interactions. But of course, you know, what's been motivated over the last 10 years by ion trap experiments of the sort that Phil showed you is a lot of work on asking how this changes when you don't just have local and nearest neighbor interactions, but you have power law decaying interactions. In particular, if the power law still drops off fast enough that you expect to have somewhat local sort of dependencies of these things. And so there's work done sort of showing the modification of these light cones if you've got an interaction that goes as 1 over the distance to some power. Okay, and these sorts of light cones are things that were discussed by a number of authors, and some of the most recent work is connected to people in RQS. So, for example, and there's been a lot of work done in Maryland and other places over the last years, again motivated by these ion trap experiments. Okay, so an example is sort of this. In fact, the first paper of this type was by Hastings and Coma, also a paper in Communications and Mathematical Physics, but in 2006. And then it was really picked up a lot by the AMO community after their first ion trap experiments with these sort of approximate power law decaying interactions. So that's sort of been quite fun. What is an interesting sort of challenge and something that I will sort of come back to in terms of experimental implementations at the very end of my second lecture, if we have time, is to think about how you could make the spreading of correlations even faster. In physical systems, people talk about sort of the ultimate limit of this being correlations that spread essentially exponentially fast. So this is for interactions of this type. So I'm just going to, rather than write the mathematical formula and suggest that that's how this looks, I'm going to say ions, decaying interactions. This thing here, what I'm plotting is something where the time scale, okay, depends only logarithmically on the distance. And this type of logarithmic light cone is something that people talk about when they think about information spreading in black holes. So there's been a lot of work in high energy physics over some time thinking about what they call fast scrambling, trying to solve information paradoxes in black holes. Is there a question?
Yeah, we have a question over there.
Thank you. Would you be able to talk about how that velocity is, what goes into that velocity and that bound?
Oh, so it depends. Yeah, so it depends on the specific system. The easiest thing to think about is if you think about sort of the excitation spectrum that you might have in a spin chain. Think about doing sort of a spin wave theory and ask effectively in your many-body system about the speed of magnons moving in that. So basically write down a dispersion relation for magnons. Or if you have a speed of sound in a say Bose gas on a lattice, then typically this velocity is the maximum group velocity of the excitations that spread through the system. So there's some subtleties of this, of course, once you start getting to long-range interactions and so on. But the best physical picture I think I can give you for this, in simple cases, spin models or bosons in a Bose-Hubbard model or things like that, is that this velocity is basically the maximum group velocity of excitations in the system.
So, and typically, I guess it will scale with the like the coupling constant between local sites and so on.
Exactly. So, so in the case of spins, okay, the stronger the coupling is, typically the higher the group velocity of the excitations is. Again, if you write a dispersion relation out, this would be effectively the maximum group velocity.
Okay. Thank you.
You're very welcome. Are there other questions? No.
It's just a small thing, but when you write down the correlation function, should we subtract that function by product of average of each?
So, so the initial assumption was that these things were decorrelated at time zero for this particular expression, I mean, in principle here. So it doesn't have to be. You can sort of look at different combinations of correlation functions in particular systems, and of course, in some cases, you might be interested in the decorrelated functions, and there would be a version of this for those as well.
Oh, I see.
Okay, so. Yeah, so there's this sort of connection to this thing here, and I'm going to come back to that later on because there's been a lot of effort in recent years to ask, can we build AMO systems with longer range interactions that will actually display this type of logarithmic light cone and will give rise to fast scrambling of quantum information. But I haven't introduced scrambling yet, so we'll come back to that at the end of the second lecture. Okay, so this is the first thing. This is correlation spreading, and that's sort of nice in its own way. The next question is, what about thermalization? So statistical mechanics tells me if I have a system out of equilibrium, it will tend to relax into some sort of steady state. I expect if I've got a closed system, and so here I've got indeed exactly that. It's something that I would consider to be a microcanonical ensemble. I've got sort of a fixed number of particles. If I think about my atoms and optical lattices up here, fixed number of particles, fixed size of the system, and a fixed energy because I'm doing sort of Hamiltonian evolution. Statistical mechanics will normally tell me that, that this will relax over some time to some thermal state in the sense of a microcanonical ensemble. Okay? But of course, this is a challenge when we think about a many-body system, because in fact, what we'd like to think about with a microcanonical ensemble is some sort of equal average over all the states sort of around the energy value that we have. And this is something that, that doesn't obviously correspond directly to what we're doing in our time evolution, because we have in an infinite system, we have an infinite number of conserved quantities. We have an exponentially large number of conserved quantities in our many-body quantum system. Because if I write down this initial state in terms of the eigenstates of my Hamiltonian, okay, then I can write my psi at t is equal to 0, okay, is the sum over n of Cn times n, so let's expand this in the eigenstates of the Hamiltonian, and then of course my time-evolved state, okay, is going to be the sum over n, Cn e to the minus I e n t times n, and these Cn's don't change, okay? So these occupations, okay, of the different eigenstates are conserved quantities, okay? And so the problem is that all Cn squareds are conserved, okay? And so how do we solve this in understanding thermalization then in a closed quantum system. And the solution to this is to think about thermalization in terms of local quantities or few particle quantities. So to think about thermalization in terms of local or few body quantities. So that you're interested in observables that are collective across the system. Normally, these eigenstates correspond to sort of highly complex sort of superpositions of states in any sort of given basis for a typical quantum system that you come across, expressing something like a projector onto N, and these are your observables that are conserved. Okay, those projectors are very, very complicated many-body objects, or they're very complicated, highly non-local objects, and normally both. Okay, and so what we do instead is we think about how local or few-body quantities tends to behave in these many-body systems. So we ask instead, okay, about what happens to an observable over time. Basically taking, obviously, psi of t, observable psi of t. And of course, we can write this, okay, as a sum over all of the n's and the m's, and we're going to have essentially a cm star cn e to the minus I en minus em t, and then we're going to have M, O, N. And so the point here is that we can look at how this thing evolves in time, and the way in which many-body quantum systems do then reflect statistical mechanics is that in well-behaved systems that are not exceptions to the general rule, that over time, all of the sort of interesting single particle or few particle and or local observables tend to relax to some sort of steady state value. And in a lot of systems that are not exceptions to the rule, those steady state values look very much like the microcanonical ensemble values for that same system. The way that we kind of often think about this is in the comparison of something that we call the diagonal ensemble to that microcanonical ensemble. And the way that we get to that diagonal ensemble is that we take a time average of this time evolution operator. So what we do essentially is we take the sort of, the average sort of value of this by taking essentially the limit as some time goes to infinity, the sort of integral over time of this time-dependent variable that we have. And this thing here is then, under certain approximations, going to be just the Cn squared times the diagonal sort of expectation values in the eigenstates of this operator. Now, what's happened here is that if we assume that the eigenvalues are non-degenerate, which is required for what I've just written down there, okay, then what's happening is that these are terms that oscillate in time, and averaging those over very, very long times is going to lead to the oscillating terms going away, and we're just left with what happens here diagonally. Now, of course, you have to be careful about the matrix elements if you have degenerate states. And then you can modify this in principle for that. And this gives you this sort of so-called diagonal ensemble. There's a question up over here.
So when you say having exponentially many quantities, conserved quantities is a problem, is it like theoretically intractable being the problem, or theoretically boring is the problem? What is the problem?
Well, the problem, okay, so the problem is by comparison with normal statistical mechanics. Because when you learn statistical mechanics as an undergrad, what we say is that many particle systems we expect to be ergodic, and the way in which they are ergodic, they forget about the initial state and they explore essentially every possible state in the Hilbert space. And the way in which we went and derived most quantities in statistical mechanics, as you sort of see them for non-interacting systems as well, is we just average over all of the different states in the Hilbert space with some sort of weighted distribution. And for a thermal state, this is a Boltzmann distribution, and in a microcanonical ensemble, what you would expect is to have some sort of average value of energy. And so what you might actually want to do is take not this, so this is a thing that we call the diagonal ensemble. But rather what you would like to do is kind of take a sum that is equally weighted over some sort of states sort of that are in some neighborhood of some sort of energy value, okay? And however many kind of total states you take there, let me just make it a big M or something like that. Okay, however many sort of total states you take there, what you'd like to do is kind of, average over the sort of value of this sort of in those states. So you would expect to take essentially the eigenstates around a particular energy value and average over the observable quantity in that region. And here we've got these kind of nasty looking sort of coefficients that come from our diagonal ensemble. And these are never going to change. So we're never going to explore other eigenstates, and we're never going to get to exactly the sort of microcanonical ensemble.
The sum is over each symmetry sector?
So the sum is over the different energy eigenstates of the Hamiltonian.
I see.
In both cases. And here, I'm summing it with the weights that corresponded to the expansion of my initial state in the basis of energy eigenstates. And in the other case, I'm just summing over eigenstates in a particular region. So let me actually, okay, that looks highly theoretical. Let me actually give you a picture of this, which I hope is going to help. So we're going to go back and think about the Bose-Hubbard model, okay? And the Bose-Hubbard model near the ground state has sort of two regimes. The superfluid regime, where the kinetic energy is much larger than the interaction energy, and you get large sort of off-diagonal correlations. And the mod-insulator regime, where you get an energy gap. This is where you've got a commensurate number of particles and lattice sites. Energetically, here, the atoms wanted to delocalize. Why did they want to delocalize? It's because of the hopping term, because they want to minimize their kinetic energy. How do they minimize their kinetic energy? They go to k is equal to 0, which means they spread out over the lattice, okay? If you want k is equal to 0, you want to be localized in momentum, you've got to be delocalized in position. So this is how they spread out. In this other case, where you've got commensurate particles and lattice sites, they want to avoid ever putting a second particle on a site, which is unavoidable kind of in this regime. So instead, where they go is into this insulating regime, where if you've got a commensurate number of atoms and lattice sites, then, and you've got U much larger than J, this doesn't want to hop on top of this. There's an energy penalty here. There's an energy gap, which for strong interactions is approximately equal to the interaction. And you get exponential decay of these sorts of correlation functions. So that's the mod insulator regime. And what we can do in thinking about this type of thing is we could say, well, what if our observable we were interested in was the kinetic energy of the system? We want to think about thermalization of the kinetic energy. Then what I would do is I would look at the expectation value of the kinetic energy in the eigenstates of the Hamiltonian. So this is what I've done here, just in an exact diagonalization calculation with 10 particles on 10 lattice sites in the Bose-Hubbard model. Okay, and what I'm plotting here is simply the lowest 500 eigenstates and plotting their energies. And what I'm going to do here, U is equal to 0, and so this is a straight line. It is trivially a straight line because U is 0, and so the only term is the kinetic energy. Okay, so at this point, the expectation value of the kinetic energy is the same as the expectation value of the energy, because this is the only non-zero term, okay? But if I go on a little bit, okay, then you can see what happens as I start to increase u, okay? And now I can sort of start to ask sort of sensible questions. My u is now 1.6 times j, okay? So here j was 1 in this calculation. And so if I had populated then some states sort of around the sort of, middle of this or up here, I can start to ask, what makes sense? And where is my sort of diagonal ensemble going to look like sort of a microcanonical ensemble? Where is it going to be that the sort of value of the kinetic energy as a function of the energy varies kind of sufficiently smoothly that it doesn't really matter exactly what distribution of states I populate? Where does it not matter exactly what the value of the CNs are, because irrespective of what the exact values of the CNs are, I get a kind of a similar description. And of course, I can even extend that out and really push the boundaries and ask, well, where would it look the same as a Boltzmann distribution? Okay, which of course is not what we expect in a closed system, but you could also make that comparison. And in fact, what you probably can't quite see in that plot is I've plotted an additional grey line, and the grey line is the kinetic energy predicted by the Boltzmann distribution when the average energy in the Boltzmann distribution is what I have in the horizontal line. You see all of these things agree beautifully, because the relationship between kinetic energy and the energy eigenstate is basically a straight line with some small fluctuations around it. Now, if I keep going on increasing u, of course, at some point I get towards the transition between the superfluid and the mod insulator, and here I've just gone across that transition. Now there is a very clear energy gap. Of course, to really see it, I would look at scaling with system size, but here there is actually now a finite gap even if I do scale the system size, and eventually this whole thing becomes a mess. And in these sorts of scenarios, okay, you now see it's going to matter enormously exactly which eigenstates I populate, because if I populate sort of a whole lot of things in this branch here, it's going to give me a very different value of the observable to if I populate a whole lot of things in this branch up here, okay? And so a lot of our understanding of where this looks like normal sort of statistical mechanics is based on the question of under what conditions does this kind of diagonal ensemble, the expectation values with the actual weightings of the eigenstates that are populated at the beginning, look like a microcanonical ensemble, which is just kind of an average over the things that you would have in a sort of a narrow window of energies. Kind of take a slice at a fixed sort of energy out here and have a look at what you get. And so there is this famous sort of statement, which is which can be phrased in a number of different ways, which we know as the eigenstate thermalisation hypothesis. And the idea, so the term eigenstate thermalisation was coined by Mark Srednicki sort of in the mid-90s. And he and Marcus Regol wrote some very nice papers on this type of thing. In particular, there's quite an accessible sort of account of this in this paper, Regol and in Nature 452, page 854. That's a 5 there, sorry, 854 in 2008. So the idea of the eigenstate thermalisation hypothesis is exactly this. It's that kind of the time dependence of this as t becomes large is microcanonical. Okay, if up to small fluctuations, and then I will say most importantly, in practice, okay, if this expectation value is smooth within, and that's basically the intuition that we've just got here. Here, where we're at, this is definitely not smooth within. This is very nicely smooth within. So here, this is smooth. It's becoming not very smooth. It's definitely not smooth up there. Okay? And so this, in this observable, the system satisfied this requirement for sort of before the transition, and it doesn't satisfy it very well after the transition. And then kind of second criterion, what you would really like for a mathematical proof of these things is that this thing, the off-diagonal elements of this in nearby states sort of becomes, well, in all states, becomes exponentially small with increasing system size. So what I would say is that most often we tend to calculate these things in relatively small finite systems, and we're not as sort of focused on this thing here, because if things relax, they will tend to relax to the sort of average states. And so it's really this kind of smoothness within that I think gives us the best intuition. But if you really want to prove convergence to the microcanonical ensemble and you want to get very specifically mathematical about it, then you would also need essentially an exponential suppression with system size of these off-diagonal elements to prove that this is really what was happening. There are a number of caveats on eigenstate thermalization in this sense, both that although I've been happily plotting this away for things including the ground state, okay, typically when we think about this seriously for the purposes of comparison with statistical mechanics, we try to do this in the middle of the spectrum rather than near the ground state, because near the ground state we tend to get a lot of states that are atypical. We tend to get gaps that open and things like that do strange things. So it's normally the middle of the spectrum that we start to compare things with if we're really talking about a study of thermalization. But of course, in real experiments, we might be interested in questions like, if we put a bit of noise into the system, we excite it just a little bit, to what extent does it look like it can thermalize that noise? Or to what extent does it look like it can't thermalize that noise? Okay. So that's the first caveat. The other little caveat is that, of course, there are classes of systems that very clearly do not thermalize, and there are a few particularly famous ones. So the first thing is, if you have integrable systems are systems that have conserved quantities or significant conserved quantities that are simple, that are kind of single particle and so on. So if these conserved quantities are not just these complicated many-body objects, but actually also sort of local sort of few-body terms and one-dimensional systems with strong local interactions are very much like that. There's this beautiful experiment way back in 2006 that first started studying these sort of strongly interacting 1D bosonic systems. This was the so-called quantum Newton's cradle experiment by Dave Weiss at Penn State University and his collaborators. What they did is they took two sort of strongly interacting clouds of Bose gases, separated them, but confined them very strongly with laser beams to move just along one dimension. And then they collided them, and they saw these persistent collisions and a lack of thermalization. More recently, we've realized that even in systems that are not integrable, that have sort of, generally very complicated conserved quantities, that there can be some sort of orbitals given particular sort of starting states that lead to significant persistent oscillations that tend to go away from this normal sort of paradigm of thermalization. And this has been a beautiful discovery that, to a large extent in this particular context, came out of tweezer array experiments. And so I'm pleased that Misha talked about this, but this is really a piece of many-body physics that people have really started thinking about because of these experiments. And actually, also a lot of the questions of these sort of integrable systems sort of work the same way. So with integrable systems, you will see this, if you plot your observables as a function of eigenstate, you will see this big spread in the values and the fact that it doesn't satisfy the conditions for the eigenstate thermalization hypothesis. And so the eigenstate thermalization hypothesis will tell you that those systems don't thermalize. And the same if you add disorder, and this leads you in interacting systems to many-body localization. Okay.
So I'm somewhat confused for the transition from the previous slide to this slide. So in previous slide, I thought the superfluid phase was not thermalizing because it was deviating from the center line.
Yeah. Okay, so the first thing that the first sort of caveat, okay, so firstly, the superfluid phase, what you will see here is if you put energy in here or you have a quench that leads you to kind of, somewhere here in the spectrum, that indeed that the kinetic energy will look like it thermalizes in the microcanonical ensemble. It actually will compare very nicely even with the Boltzmann distribution because of this beautiful linear relationship between the total energy of the system and the kinetic energy. So there, this is a smooth function, and so you would say that you would expect this to thermalize. Whereas in the mod insulator side, at these low energies that we're looking at, you would then not expect things to thermalize. Again, this is now no longer smooth, and so you would not expect it to thermalize. Now, in fact, if you take these models and you look not at the low end of the spectrum, but you look in the middle of the spectrum, then you can start coming up with different conclusions. So if you try to do the same things in higher dimensions or in the middle of the spectrum, just having a mod insulator as the ground state wouldn't necessarily bother you. You could still thermalize in that middle part of the spectrum where everything was highly excited and you were no longer worried about the gaps. But in 1D, you would still have the problem of strong interacting systems having typically a lot of conserved quantities. But in 2D, this would all be quite nice and should probably thermalize quite nicely. Again, in fact, these plots that I have here came from some work we were doing specifically asking questions about thermalizing small amounts of energy sort of beyond the ground state and showing why it looks like things thermalize quite nicely in the superfluid, even though it's quite close to the ground state, which is kind of a little bit of a surprise almost. A couple of questions right there.
Hi, yeah. Thank you for this first lecture here. Just maybe a clarifying question. Like, let's say I had some system and I was like, I want to prove that this system thermalizes. I guess like what operators do I have to study and like show that I either have these like small diagonal elements and exponentially decreasing like off diagonal elements to like say, hey, I thermalize or not?
Okay, so I think that, so what I should do is give you a practical answer to that question and say that in an experiment, there are a certain number of things you're going to be able to measure and that you're going to be interested in measuring that will characterize dynamics in the system that you're interested in. Mm-hmm. And I would pick the observables that you can measure in the experiment and the observables that you'd be interested in. So this is typically, so in a cold atom experiment, this is going to be the momentum distribution. It's going to be, sometimes when you look in, with a microscope and you measure sort of, you can measure higher order correlators of sort of density up to sort of, multi-body operators. And those types of things. But essentially, the thing is, stick to things that you're interested in practically in the experiment and stay deliberately away from the things that are conserved quantities because they commute with the Hamiltonian.
Okay, so it's not like I would pick every single observable, if my observables were Pauli spins, I wouldn't try to study every single expectation value of some spin operator. I would say, hey, in some practical system, I have some number that I can probe somewhat reliably, and I'll study just that subset and then just make and say, hey, from this subset, I know maybe with this amount of certainty, with this indication that I thermalize.
Yeah, so to give you a concrete example, so people are interested in experiments with cold atoms and optical lattices in looking, for example, at spin models, okay, maybe with multi-component gases. And so there you might start to be interested in effective sort of momentum distributions from the particles when you release them from the system. You'd be interested in spin-spin correlations that would characterize the different phases that might be there in the model. So for example, with two-component bosons, I can make, say, a spin one sort of spin model that might have for example, XY ferromagnetic phases, and it might have a Z antiferromagnet phase, and so on. So all of these are going to have sort of correlation functions that characterize those phases. And now if I was pumping energy into the system and asking, was it able to thermalize that energy, I would say, well, what are the relevant correlation functions that I might want to measure in the experiment to characterize those phases and to do the things that I want to do with that system? And does it look like those quantities have thermalized? And so should I describe what's going on with the heating of the system in terms of, that I simply heat the system into a thermal state and that sort of higher energy, average energy, or higher temperature, effectively, if you like, corresponds to a change in the correlation functions. And what you find, of course, in a number of these cases is that, that in fact the system is integrable, or that you're so near the ground state of something that is otherwise non-integrable, and so the middle of the spectrum would thermalize, but near the ground state it doesn't. And in fact, in many cases, that gives you better results in the experiment to what you would expect if you could actually properly thermalize all the energy.
Cool. Thanks so much.
So I want to understand what's the relationship of advantage between the quantities we've talked about. So it seems like, in particular, with the diagonal ensemble and the microcanonical ensemble, they coincide when we have our U low. And as we ramp up the U, they start to diverge, right? But then as we ramp up our low U, isn't it more classically simulable anyways? Like it seems like it's less correlated in the first place.
So I would say that, so in this particular case, all of these things are relatively well classically simulable. So this is a very good question. Normally, once you go over towards a thermal state, there are methods, in particular for these bosonic systems. If you do thermalize, then things will generally be fairly classically simulable. If you have things that don't thermalize, then it's much more often sort of hard to capture exactly what those dynamics are going to be. So what I would say in terms of these things, and I can maybe put up a plot that I was going to put up in the second half of the lecture, sort of anyway, and this is the following sort of idea that in some sense that what you will find as a function of time, if you take a system and you have a quench and it's out of equilibrium, that initially there might not be very much entanglement. It might be therefore relatively simple to simulate. So this is, if you like, the difficulty of classical simulation as a function of time. It might be sort of low, and this will eventually kind of start to grow and grow as you look at really a genuinely out of equilibrium system. And then at some point, sort of, once it sort of settles into some sort of steady state, it might be much easier to look at this if that system does properly thermalize, or if there is some, sort of simple way to describe the sort of state that it relaxes into. So this is kind of what you have. You have this kind of region in the middle where it's sort of very difficult to simulate classically, but normally at short times or at later times, if it does thermalize, you tend to be able to simulate it. Now, in terms of the level of correlation, of course, in the specifics of the mod insulator regime, if you're in these if you're within these branches and you know where you are, there may be simpler ways to do that. So I would consider that to be a specific example of something where you might be able to simplify the classical description and make it easier to simulate because of that. But in general, the things that become easy to describe classically are the sort of the thermal states after things have relaxed.
So does that mean that the thermalized quantities are not necessarily good candidates for advantage, right? Like we really should be caring about the intermediate time dynamics and not the end states or beginning states.
So that's absolutely true. In these sort of dynamical calculations for the things that we can sort of calculate with, for example, matrix product states in a time-dependent form, that's exactly right. Short-time dynamics we can calculate, and there are often ways, if you're allowed to assume that the system thermalizes, to get towards what these sort of states would have to be sort of at late times. And so the regime that's really difficult is the sort of intermediate regime. Now you might ask, well, why am I interested in those intermediate dynamics? And it's precisely because, of course, there are some systems that you can then drive sort of permanently a little bit out of equilibrium. And trying to find transport coefficients, for example, in certain types of systems involves sort of driving them so they're permanently a bit out of equilibrium. And so for some systems, that appears to be more in this regime, although people are trying to find ways to try to get it sort of down to here in terms of their calculations. But that's the sort of thing that you might be interested in generically that is in that kind of intermediate out of equilibrium regime.